first point I want to discuss today was an outcome of the question of Matteo did last time, but he's not here. I answered. I mean, already get the answer.
Too bad for him.
But now I give the proof of my answer. It is this. Consider that you have an algebra and a state on that algebra. And you construct the GNS representation, which is made by a Hilbert space, a representation of the algebra in the Hilbert space, and a cyclic, we can call it vacuum, is a physical notion of vacuum. It's just a mathematical notion. The GNS vacuum, we can call it, is the cyclic vector of the representation. Then the question was, what about purity? Because you always heard speaking about if a state is pure or not. And because there is this idea that a state which is pure is a vector, and a state which is not pure is a density matrix. This is the standard way of thinking of it. So let me remind you, what does it mean pure? A state is pure if it cannot be written as the linear combination, convex combination of two other states. If you can find two other states, so positive linear functional on the algebra, such that you can write this state as the superposition of two other states, the state is called mixed. If you can't, the state, the state is pure. Okay. This is a notion which enters, of course, very much in studying quantum black holes and things like this. So these are the two possibilities. Either one state is the convex combination of other two states, or not. So if you think of the set of all states as this set, states which are here, you can write those as combination of these two. These are mixed. These extremal states are pure. And now we want a characterization. So you have an algebra state and the GNS construction. How could you decide if a state is pure or if it's mixed? Okay, that is the question. So I remember, so a representation, remember the definition of representation is a map of the algebra into the bounded operators in a Hilbert space. An operator in a Hilbert space is a map, a linear map from the Hilbert space in itself. Okay? It is bounded if the norm of ape C is less or equal than the norm of C. So the map of the algebra into the bounded operator in the Hilbert space is a representation if it preserves the algebraic relationships. Means if you have product of two elements of the algebra, this is the product of the elements of the representative. Also, indeed, we have to add this condition because I mean, the image of the identity can act as the identity on the image of the algebra without the need of coinciding with the identity. This is an extra assumption. This I was not precise in answering to your question the other day. And of course, it preserves also the star. It is faithful if it is one-to-one. And now comes the notion which is important. It is irreducible. A representation is irreducible if the only subspaces invariant are 0, the 0 vector, and the Hilbert space itself. So this is the key notion, the irreducibility of the representation. So what, there is, first thing, there is an important lemma, which is called the Schur lemma. Which says the following thing. Give yourself an algebra and a representation of the algebra into the bounded operator on a Hilbert space. The commutant of the algebra, the commutant set, as the name says, is the set of all operators C belonging to the bounded operator on the Hilbert space H, such that C commutes with every element in the representative of the algebra. Okay? This is the commutant. The Schur's lemma says that a representation is irreducible if the commutant is just made by the identity operator. You represent your algebra in the Hilbert space. Look for all the elements in the bounded operator which commute with the representative of the algebra. If you find just identity operator, the representation is irreducible. If you find more than identity operator, the representation is reducible. Okay, this is the lemma of Schur. The proof is quite simple. How do you prove this? Suppose that this is not true, that the commutant of the algebra is made by certain operators. Suppose there is an operator C, which is not identity, belonging to the commutant, means that C, as I say, is, commutes with every representative of the algebra. If C belongs to P, to the commutant of the algebra, also C star belongs to the commutant of the algebra. And you can consider C plus C star, which is self-adjoint. So you have a self-adjoint operator, which we may call, I don't know, C1, self-adjoint, which commutes with the representative of the algebra. But a self-adjoint operator, you can resolve its spectrum. Suppose, for instance, that psi is an eigenvector for C, for C1. Then, if you apply the whole algebra to psi, and because P of A commutes with C, this is P of A C of psi, lambda P of A of psi. So the whole algebra applied to this vector belong to the same eigenspace. So if the commutant includes a self-adjoint operator, the spectral projections are invariant subspaces for the representation. Yes?
Sorry, what's the symbol you used for the commutant?
This pi of A prime.
Oh, okay, it's just, yeah.
A is the algebra. Pi of A is the representation of the algebra. The commutant is this prime. So this is the direct proof. If the commutant is not just made by the identity, you can construct invariant subspaces by taking the spectral projectors of the combination of C and C star if C belongs to the commutant. And vice versa. The vice versa is also true if you have an invariant subspace, H1 included in H, take the projector on H1, the orthogonal projection of H1, this commutes with the algebra because H1 is invariant under the representation of the algebra. This is the proof of the lemma of Schur, which is the same that you have probably already seen in group theory, in representation of groups. So if you decide if a representation is irreducible by looking to the commutant of the operators of the representation. And now comes the theorem which answers to the question of Matteo of Monday. The theorem says give yourself an algebra, a state, and construct its GNS representation. The Hilbert space, the cyclic vector, and the representation. The theorem says omega is pure if and only if the representation is irreducible. This is important every time you want to discuss purity of states, of partial states, of black holes, exterior of black holes, Uru effect, as we will do. Okay. The proof is quite simple again. So, suppose the representation is not irreducible. Okay? So, in H omega, you can distinguish an invariant subspace. And by the invariant subspace, you can define the orthogonal projector on the invariant subspace. Because of the irreducibility of the vacuum, the projector applied to the vacuum is different from 0. And also the orthogonal complement applied to the vacuum is different from 0. This is a consequence of the irreducibility of the cyclicity of the vacuum. What does it mean, cyclicity of the vacuum? Apply the representation to the vacuum. This is the Hilbert space. you can generate every vector in the Hilbert space by taking linear combination of such things. Then if you put the projector here, okay, since the this is not empty. This is is different from 0. But you can commute this. And if this was 0, this would not be true. So the projector applied to the vacuum is non-zero. And the same applies to the orthogonal complement. Is it clear? Because of the cyclicity of the vacuum. Then you can convince easily yourself, since you get this property 1 minus p times any representative of the algebra times p. You commute this here. This is 1 minus p times p of a. P is an orthogonal projector, so p squared equal p minus p of a equal 0. Okay, so this implies that you can, given your state, which is by the GNS construction equal to this, this you can write 1 minus p plus p applied to c of omega, p of a, c of omega, 1 minus p plus p applied to c of omega. Then you use this property, and this is just p of omega alpha z0, p c omega plus 1 minus p c omega p alpha c of omega 1 minus p, the orthogonal projector on the orthogonal subspace, and this is lambda omega 1 of a plus 1 minus lambda omega 2 of a, where you define omega 1 equals 1 over the norm of the projected vacuum times this, because you want a normalized state. This is a state. You can show that this is a state. And similar definition for omega 2. So I wrote, because of the reducibility of the representation, it is easy to write omega as the convex combination of two other states. So the state is not pure. Vice versa, you can prove also the vice versa. This is an application of the Riesz lemma. I will give you this in the week assignment. It's extremely simple. It's one line on reasoning, but since we have many things to do today, I won't prove the vice versa, but the vice versa say, suppose the representation is irreducible, but the state is not pure. Means that you can write omega like lambda omega 1 plus 1 minus lambda omega 2. If you now can use the Riesz theorem, the Riesz duality theorem is fundamental in quantum mechanics, which says that a Hilbert space is self-dual. Means that if you consider the linear functionals on a Hilbert space, they are representative. They have a representative as vectors. Any linear functional on a Hilbert space can be represented as a scalar product. This says the Riesz lemma. if you use the Riesz lemma here, you see that lambda omega 1 can be represented by an operator that is the metric of omega 1 in the GNS product. Let's say A star B. This is psi of omega, P of A star, T, this operator, P of B, psi of omega, and you can show that this is in the commutant of the representation. So the representation cannot be irreducible if you suppose that the state is not pure. Okay, this is an easy application of the Riesz lemma. You find the details in the book I told you. It will be in the week assignment. It's the converse statement. So this theorem is very important. It tells you when a state is pure. We constructed last week on Monday, we construct the unique representation of the Weil system, means the Schrödinger representation of quantum mechanics. I showed you that this is irreducible. It's an irreducible representation, and this means that every vector in the Hilbert space of the Schrödinger representation defines a pure state, and this was the statement Matteo was mentioning. Every vector in an irreducible representation defines a pure state. This is what you normally see in quantum mechanics book. And a state which is non-pure is represented as a density matrix. Okay, so this concludes what I want to say on the sister algebra formalism in quantum mechanics. Now let's continue. Now we enter in our main direction. So this, you find this theorem and all the things I said about sister algebra, including the proof of von Neumann theorem, here. I'll send you the reference by mail. If you have difficulties in finding the chapters, tell me, I will give you the book. The lecture of today, there I will send you the notes, my notes. So let's start again what we were doing last week. So we are considering the classical Klein-Gordon question. And we were considering here the Cauchy problem, means that we are giving initial condition on the field and on the normal derivative of the field to the time zero surface. By Fourier analysis, we saw that this problem, which is the initial value problem, can be solved by using the so-called Pauli-Jordan function, whose integral representation is most easily written in Fourier space. epsilon is the K0 is the sine function. Okay, and if you give yourself this function, by the way, you construct it by Fourier transforming the equation and the initial data, the solution, the unique solution to that problem, you are supposing that these are functions compactly supported. C0 infinity is the set of functions on a set that you write here, which may have real or complex values, which are infinitely differentiable. All that you can differentiate an infinite number of times, and which are vanishing outside a compact set. Okay? They are zero everywhere, with the exception of a compact set, a set which is closed and bounded. So using the Pauli-Jordan function, you write the solution this way as a convolution, a three-dimensional convolution. You convolute the Pauli-Jordan function with the G function. And the time derivative of the Pauli-Jordan function with the function itself. In such a way, since the Pauli-Jordan function, as we will see later in this lecture, is zero in the complement of the light cone, this function is zero if x squared, which is x0 squared minus x squared, is negative, means this is R4, this is the light cone, the Pauli-Jordan function is zero here. If you give yourself compact initial data at time zero here, let's say, the solution of the Klein-Gordon equation you are constructing is supported this way. Okay? Draw the light cone in every point of the initial data, and the envelope is the support of the solution. The solution vanishes here. It's a causal propagation. Okay? This is standard. Now, the Pauli-Jordan function solves itself in the sense of distributions, this equation, with respect to any of the two variables. Let's say it solves in the difference variable. Okay? This means that if you consider the convolution of the Pauli-Jordan function with a compactly supported function in the space-time now, I am integrating not only the space but also the time. So think that you have here a space-time defined function f of x. This is its support. Now take this convolution. Okay, this is going to define for you a function which is defined in a set like this, and this solves also, let's call this psi of f. Psi of f is a solution of the Klein-Gordon equation also. Okay, so there you see one way of using the Pauling-Jordan function to construct a solution of the Klein-Gordon equation given the initial data, given the compactly supported initial data. Now I give to you a test function, let's call it like this. This is a function defined on the spacetime, maybe real, maybe complex. Take the convolution with the Pauli-Jordan function. Now it's the 4-dimensional convolution. It is obvious that this satisfies also the Klein-Gordon equation. You see? Because if you apply this operator here, this operator is just applied in the x variable. It enters the integral because this is compactly supported. It applies to the x variable. And this is 0 times f, means 0. Okay. Now the theorem, which I want to show to you, which in a sense is at the basis of everything I will say after, is that every solution obtained this way can be written like this. If you give yourself, call S the space of solution of the Klein-Gordon equation with compactly supported initial data. Give yourself the function at time 0, and the time derivative of the function at time 0 with compact support. You get that formula, but now I want to show to you that there is a way every such a solution can be written like this. Of course, this f is not the same f than there. It's another function. We are going to construct this other way of solving the Klein-Gordon equation. To do this, I remember to you the other time we splitted the Pauli-Jordan function into the difference of the retarded and the advanced propagators. Okay? Remember that the retarded and the advanced propagators solve the inhomogeneous Klein-Gordon equation I only use the name propagator for distributions solving the equation with a delta term here, while in certain contexts you can find the name propagator also for this function because it propagates the initial data. But in quantum field theory, you call propagators solutions of this equation, and of course perturbation theory is based on the use of the time-ordered propagator, which is a third way of solving this equation. The retarded propagator is obtained, as I told you. This is the support of the D function. The retarded propagator is the D function times theta of x0, and the advanced propagator is the D function times theta of minus x0. So you split the x space support of the commutator into the forward and the backward part, and you call retarded this part and advanced this part. Okay, in such a way that you have this difference. Remember also the integral representation. So the first statement is that every solution of that problem can be written in this way. Okay. How could we proceed? So consider a solution of the Klein-Gordon equation whose initial value have compact support. Okay. And give yourself a function QFT, which is some sort of smoothed out Heaviside step. It's a function which is 0 if t is less than 0, 1 if t is bigger than 1, and smooth in between. Okay? And consider the function f okay. So this is a function of t, let's say. This is a function of t of x. This is the solution of the Klein-Gordon equation we have started with. This is this step function, and you apply the Klein-Gordon operator to it. You see what it is? First statement is that f has support which is compact.
Can I have a question? Your chi is 0 if t is less than 0 and 1 if t is greater than 1. What happens between?
In between, it can be whatever you want. But think of this. Why this so compact? You see, when this is applied to both this function. When you apply the differentiation to this function, this vanishes everywhere with the exception of the interval 0, 1. When the whole operator is passed to psi, this is 0 because psi is a solution of the Klein-Gordon equation. This means that the support of this function is contained. See, this is the support of your solution, and this is 0, 1 is contained here, the support of this function. Okay. So this is a compactly supported function, and I will now show that you can use this function to reconstruct this solution. Take my notes with me. So the point is that we are going to use the property, if you want to solve the inhomogeneous Klein-Gordon equation, a solution to, let's use another symbol here, phi, AF is the solution of this equation, which has support here, and RF is the solution of this equation, which has support here. What is AF is the convolution of G advanced and RF is the convolution of G retarded with the source. Is it clear this? Because when we apply the Klein-Gordon operator to the retarded or the advanced propagators, we get a delta, and then we convolute this function with the delta, and this gives back f. Okay? Did you follow? So we are going to do this with that function. So, for instance, call f, we are called f that function. Okay. But what is f? F is itself the Klein-Gordon equation applied to chi of psi. Are you following? So you would like to, you can say that R of f is chi of psi plus a solution of the homogeneous equation. I say it again. I produced there a function which has compact support. Now I use this function having compact support as source in the Klein-Gordon equation for an inhomogeneous Klein-Gordon problem. And I'm considering in this case, the retarded solution. So the retarded solution is the convolution with the retarded solution equal to f, which by definition is equal to this thing. Okay? So by comparing these equations, I can deduce that R of f is chi of psi, but I can always add a solution of the homogeneous equation. Okay. Which solution of the homogeneous equation? It has to be that solution of the homogeneous equation such that this thing has the right boundary properties. Means it has support in the future of the initial data. And so you see that R of f is just equal to chi of psi without computing it. If you want to compute the retarded propagator applied to that initial data, this would be an hard task because there is a boundary inside. You cannot push the integration to infinity. But because of this argument, you can say that the retarded operator applied to f is just chi of psi. If you do the same argument to the advanced, so that the Klein-Gordon equation applied to AF equals f, you conclude that AF equals, again, chi psi plus H2. And now, because the support has to be this H2 has to be psi itself. Okay. So I have computed. I gave to you one particular function of compact support. And with this procedure, I compute the action of the retarded and the advanced propagators to the function itself. Now I use this relation, EF which is the retarded minus the advanced. This is chi of psi minus chi of psi plus psi is psi. So we do conclude that if I have a solution of the Klein-Gordon equation which has compact initial data, I can write psi of f as the convolution of the Pauli-Jordan function with
Why could you set h equal to 0
in the first case,
in RF?
because chi, the support of the advanced support, no, I was wrong maybe.
For the retarded one.
The retarded support is this way. Chi has support for t bigger than 0. So if I multiply the solution psi by this step function which has support in the future, I get something which is 0 here and non-zero here. So I can't add anything here. You see?
And how does that change in?
The advanced is the opposite way.
Yeah.
So because chi of psi has support this way, I have to subtract this part here. So this is the only possibility.
But psi by itself
Psi is a solution of the homogeneous.
of the whole thing, yeah.
This is a solution of the non-homogeneous, I of f. But I can always add a solution of the homogeneous, and I add one which produces one which has support in the future of the initial support in the retarded case. And in the past, of course, there is still there is a second part in this theorem which I'm going to show now. What is the kernel of this map? There is a kernel. All the functions which are themselves Klein-Gordon operator applied to a solution are in the kernel of this. And the third part of the theorem, which I'm going to show now, is the one which is important for us, which relates the so-called Klein-Gordon products, which is at the basis of all the treatments you have already seen of quantum field theory in curved space-time, to this Pauli-Jordan function. Because I'm going to rewrite an inner product using this theorem in terms of the usual Klein-Gordon product.
So there is no solution to the Klein-Gordon equation, the homogeneous one, which have support just in.
They have to be compactly supported. The arbitrariness could be functions which have just support inside here. I will tell you now about this. Is this clear? So the point is that every solution which is which has compactly support initial data can be written this way. This is the thing you have to keep in mind. That's the only thing. This is a solution of the Klein-Gordon equation, and every solution of the Klein-Gordon equation can be written this way, provided it has compactly support initial data, of course. Yes?
Shouldn't that be dx minus y, not ex minus y?
Excuse me?
Should that be dx minus y?
Dx?
The last line you just wrote, psi f equals integral ex minus y fy. Shouldn't that be a d?
dy.
No, I mean, why did we define E as a function over spacetime?
D, sorry, yes, D. But it is conventional to call this map EF in books.
Yeah.
Okay. Because this is going to be true also on curved spacetime, where you don't have the Pauli-Jordan function, but something else, of course. But this mapping is also true for globally hyperbolic spacetime. So everything I'm saying goes through to field theory on globally hyperbolic curved spacetime, in which, in this case, you will have the analog of the Pauli-Jordan function and the splitting of it into advanced and retard propagators. Okay. So the first statement you have to keep in mind is that this describes all the solution of the Klein-Gordon equation. So, to come to your question, what is now the set of solution such that E of f is 0? Okay. The ambiguity in choosing the function. Allora, E of f is 0 if and only if f is the Klein-Gordon operator applied to another compact support function. Okay, the direct implication is obvious. So if you write d of x minus y applied to this, here you can integrate by parts. This is 0 and this is 0. So if f is like this, E of f, which is the convolution with the Pauli-Jordan function, is 0. The converse, suppose EF is 0, means that RF minus AF is 0, means that RF equal to AF, and this is only possible if both RF and AF have support here. Okay, and this means also that the Klein-Gordon operator applied to RF equal to F, so we have exhibited a function which has compact support such that F is the Klein-Gordon operator applied to it. This is the second part of the statement. And the third part of the statement is our starting point towards quantum field theory on curved spacetime. So let me say it again. We have seen that if you have a solution of the Klein-Gordon equation, which has compactly supported initial data, you can always write it, this solution, this way. Okay? Where f is what you would call a test function. It's just a function. A function defined on your Minkowski space-time, which may have real or complex values, depending on what you are doing. Think of it as a real function, but it can be also a complex one, if you are studying complex solution of the Klein-Gordon equation. Now, let's introduce an inner product in the space of such compactly supported functions, which is just, let's say, for instance, real functions. Okay. We have the Pauli-Jordan function. We have seen its role in solving the Klein-Gordon equation. We have seen that if you make a convolution of the Pauli-Jordan function with any test function, this provides for you a solution of the Klein-Gordon equation, and every solution is like this. Now let's consider this inner product in the space of test function. We want to compute it. Okay. This is the source of the so-called Klein-Gordon product that normally you see as given. It comes from the structure of the space of solution of the Klein-Gordon equation. Let's see how to compute this thing. We already see, so if we make this integral, we know that this object integrated by this, I can call it psi g, let's say, and this is a solution of the Klein-Gordon equation. So this integral equals, let's do it on this other blackboard. So Fg this is equal to F psi G where psi is the solution we have just discussed. Okay. So F, by hypothesis, has compact support. Suppose that you can find an interval T1, T2, such that T1, T2 times R3 contains the support of F. This is the support of F. This is T2. This is T1. So this integral is equal to the integral from T1 to T2, the integral over R3, the same thing. Okay. Now I can use F as the source of a Klein-Gordon equation with source. Okay, so I write check this step. I write F as the Klein-Gordon operator applied to RF, let's say. Is it clear? Take the retarded convolution of F with the retarded propagator, apply to the Klein-Gordon operator. This gives back F itself. So this integral equals the integral from T1 to T2 dt, the Klein-Gordon operator applied to RF of x, psi g of x, dx, d3x. Okay. Now let just be complete. Observe that the Klein-Gordon operator applied to a product, let's say Fg. This is d mu Fg. Let's say, no, apply to the first. I want to make this operator to pass to the second, just by a formal manipulation. This is equal to d mu of Fg minus d mu F d mu G. Do you see? I have just added the derivative of G and subtract it. Okay? And then I can also make this enter inside here. This is d mu of let me see.
That doesn't cancel out.
It is made for. Wait, I'm wrong in writing this thing. This is d mu F G. Okay, now it works. Minus this, because when I apply this to the first, I get back this. When I apply this to the second, it cancels this. And now, I make this passing through here. This is going to be d mu F, d mu G.
That doesn't cancel. It's
I'm
on the
wrong.
right.
Okay, let's do it again. D mu F. So this is d mu F, say, G. When I apply an extra d mu here, this is going to be d mu F times G minus d mu F d mu G. Okay, so that this is equal to this minus d mu f d mu g. Is this correct? And then I have to do it once more here. This is d mu f times g minus f minus d mu f d mu g plus f the Lambertian of g. Okay, now I'm there. You see, so that the Lambertian of f times g is this current d mu f g minus f d mu g plus the Lambertian of g times f. So if I add m squared here, I get m squared here. And if I apply to my formula there, since psi is a solution of the Klein-Gordon equation, this term disappears. So I get here, this is going to be equal to the integral to t1, t2, dt, the integral over d3x d mu of d mu rf psi g minus rf d mu psi g. Okay? So I can do this integral, and you see that the integral RF has support this way. Here there is the surface t equal t1, and here there is the surface t equal t2. I apply the Stokes theorem to this integral, and the integral on this surface vanishes because the function is 0 on that integral, and I just get the integral on this surface. So this is equal to the integral t equal t2 over d3x d over dt over f times cg minus rf d over dt cg. Okay? The final step is that on this surface, AF equals 0. AF is the solution of the inhomogeneous Klein-Gordon equation, which has support backward. So I can always add an A here. So in the final step, because A is 0, I can write here R minus A F, R minus A F, and R minus A F is precisely EF, the retarded minus the advanced propagators. The advanced propagator convoluted by F on this t equal t2 line is 0. So I can always add 0 to this equation. So the final result is that this is equal to the integral of, now I can say t2 is, now in the final formula I can move t2. So I get d3x d over dt of psi f, psi g, minus psi f d psi g over dt, where psi f is dx minus y f. Okay, you see appearing the Klein-Gordon product.
What happened to the spatial derivatives?
What happened to the
Spatial derivatives.
I mean, I used the Stokes theorem. And since I used here the surface t equal constant, the only term that survives here is the derivative with respect to time. Had I used a curved space-like surface, I would have write here a more complicated formula. But because I've chosen just t equal constant, this reduces to the derivative with respect to time. It's Stokes theorem, you know, d mu g mu equal the integral of g mu ds mu. Volume, boundary. Okay? So, this is the starting point for quantization. But you see, it's a structure which is inherent in the space of classical solution of the Klein-Gordon equation in such a way that you can even write it formally this way. We have constructed the so-called Peierls bracket, which are covariant version of the Poisson bracket. And they are simply given by the minus the Pauli-Jordan function. Why minus? Because when you want to do equal time Poisson bracket, you make the derivative with respect to the second argument. And since the derivative with respect to time of d is delta, the minus sign guarantees that you have this Poisson structure here. This is three-dimensional, okay? But these classical parentheses are just the structure which is induced in the space of solution by the Pauli-Jordan function, which is the unique solution of the Klein-Gordon equation subject to canonical condition, okay? So what will be now quantization? Exactly as in the finite dimensional case, now we arrive here. Phi of x, phi of y is minus d of x and y. Quantization will be changing this classical algebra into a quantum algebra, which will say that phi of x, phi of y, what is the distinctive feature of a quantum algebra is the appearance of an I here. Minus I in dx minus y. So our next task is to construct an algebra of operators such that the commutator is given by the Pauli-Jordan function multiplied by I. Okay? This is what we do next. So 5 minutes break.
How did we get from the FDG bracket over there to the phi x phi y bracket over there?
Excuse me. Which?
Sorry, I'm not sure why, how we got that bracket there.
This formula?
No, the x phi y equals
Here. This is in a sense a summary of this. I have not the time to explain the mathematical details of the meaning of this because this would be an infinite dimensional Poisson algebra and it requires a lot of mathematics to really do it. I don't want to do it. But what I want to show to you is that if you use such object to construct let's say, symplectic structure in the space of classical solution, then we go to exactly as we did in the finite dimensional case, to a quantization of this algebra simply by multiplying by I. Okay? And then this, studying this problem will, if we really understand this problem in the flat space-time, curved space-time is no different. Really nothing different. Nothing special.
Could you tell us?
I still don't understand.
find some instances can be contained twice.
It is
Without break.
50
Yeah.
You're proving Schurzlemma?
Schurzlemma, I just cut it. So
you just usually beat once.
So you said that we have an invariant subspace psi, side by side.
yeah, where?
So you said C1.
Yes, because it is at adjoint with us.
Yeah.
So like for projectors, those are invariant on the diagram.
Same course, I guess.
Because it commutes.
And you're like 2 hours.
Okay, yeah.
One important function, the Pauli-Jordan function. Using this Pauli-Jordan of test functions, what is the space of test function? Is the algebra of compactly supported functions defined on your manifold. In a way, it's describing the geometry of the manifold. And I can set up a symplectic form here inside, this way.
Please turn on your microphone.
Wow. So you can see this form as a form on the algebra of functions on your manifold. And as we saw in the first lecture, this describes the classical geometry. Or you can see this as defining the Klein-Gordon inner product in the space of solution of the Klein-Gordon equation. I'm talking about here real solution for the moment. They are the same thing. There's no difference between these two things. Or in a covariant way, or in a formalism in which you have made a 1 plus 3 step leading to the canonical formalism. So this is maybe an approach to quantization that was initiated by Peierls, but then it remained more or less not used. And this is the standard canonical approach to quantization.
Can you just say the 2 ways to interpret that again? As a form on when describing our geometry? Sorry, I just missed the word.
Because this is the commutative algebra we were discussing in the first lecture of functions on a Hausdorff space. which is supposed to describe the geometry, the classical geometry of, yes?
Wait, you said this is the form for the complex functions?
Compactly supported initial data.
Yes, but the functions have complex values.
Excuse me?
But the functions take complex values, right?
Can be real or complex. For the moment, here I'm discussing real. Then when I put here comps and conjugate, we get some I here, something. Okay. But my aim, I spent 1.5 hours of time to convince to you that this form does not comes out of the blue. It is inherent in the structure of the space of solution of the classical Klein-Gordon equation. Now, quantizing the theory. So if we write these things, so I can write it in a covariant way, this way. I do not distinguish here between, I cannot explain the true mathematical sense of this parenthesis here, because it would lead us too far. Or you can write in a exactly equivalent way, equal time Poisson brackets. Okay. This is an infinite dimensional generalization. Of course, there are mathematical problems in doing it to the Poisson brackets of the canonical variables we have discussed in the quantization of systems having a finite number of degrees of freedom. But this formulation is equivalent to this covariant one in which you do not distinguish between, yes?
So actually, I have a question. So d of x, so d
is the Pauli Jordan.
It's non-zero inside the light bulb, right?
Minus, there is no I here.
Yeah.
Sorry.
So it's non-zero inside the light bulb.
Is 0 outside the light cone.
And non-zero inside the
And
light bulb.
non-zero here.
Yeah. So if say x0 and y0 are the same, but x and y spatially are not the same, then why is the Poisson bracket of phi at tx and phi of ty 0?
Because this is a relativistic system.
Yeah.
It is a symplectic structure. It will be, then it will be translated in the commutation of the operator at space-like distances. It is translating the relativistic invariance of the theory. By the way, it is also true here.
No, so I'm just wondering, because if tx and ty are both inside the light cone,
Tx and
so you just
cannot be. At fixed time, they are space-like.
Yeah.
The same time.
Okay, so
the light cone of Tx and y is there. And that's not clear?
okay.
Because the time is the same here, you see? Okay. You agree? So it is translated in this single formula. So quantizing would mean, as I said, transform this algebra into a non-abelian one, and this is done by just the appearance of this little y, little I, which makes this object into operators. Okay, and this also has an Hamiltonian counterpart in which you ask for equal time commutation relations which are the starting point of canonical quantization in any standard textbook of quantum field theory. Now we are describing a system having infinitely many degrees of freedom. The degrees of freedom are parameterized by the space-time variables, by the space variables, by the way. So we do not expect the uniqueness theorem to hold, and indeed it will not be true. Okay, so we want to construct a representation of this canonical commutation relation now, and the first one we are going to construct is the standard one. Okay, and then we will discuss other quantization, mainly the KNS quantization, which is a non-pure state in the case, describing thermal quantum field theory, but it will be a representation of the same algebra. The canonical commutation relation in this form or in this form hold in any quantization, but we are going to construct inequivalent Hilbert spaces. Okay? So next task is to review.
Why is the canonical? Why has it become more standard?
Excuse me?
The canonical approach. Why is it has it become more standard than the IELTS one? Is it because when there are constraints?
Accident of the history.
Is it just that easy for Maxwell fields? And
I mean, the format is maybe not really practical from if you want to really do computation. Of course, there was 170 years of Hamiltonian classical mechanics behind it. So you don't start building on nothing. You go. The first one make a step in a direction, and then everyone goes that direction. It is not obvious that it will be the good one, but I mean there is a covariant formulation also at this level, which do not distinguish between position and momenta. And also with this, I'm answering to another question that Matteo did post the other day. What about distinguishing? By the way, since we are constructing here a relativistic invariant quantum theory, distinguishing time and spaces, then you have to work to show that the theory is relativistic invariant. If you start from scratch with something which is invariant, at every step you have something which is invariant. Okay, but I will maybe shortly review the standard construction you are familiar with to see that there is a particular realization of such canonical commutation relation, which is the one which is described in every book of quantum field theory, and then we can build perturbation theory and all those things. So, but first, I would like to show why, when you want to quantize a field, if I use this hat, or maybe I don't use it, you understand from the context that I'm speaking of something which is an operator in a Hilbert space. Why this object cannot exist as such? Why quantum fields are singular objects? Okay. Suppose to discuss this issue, I should maybe tell you what are the general properties you are using when you build quantum field theory in the standard sense you are used to. Okay, you can translate such properties into a set of requirements which are called axioms. But when you call those properties axioms, in a way you are reducing their meaning to just a mathematical statement. It is not this way. They are just expressing basic physical requirements. So there are requirements that comes from being a quantum theory, and are requirements on the states of the Hilbert space. You are asking for a separable Hilbert space of states in which you do have a strongly continuous representation of the translations, which is generated by the energy momentum operator, and you ask that the spectrum of the energy momentum operator is contained in the forward light cone. What does it mean? This means that the energy has to be positive for every inertial observer. If you don't ask for energy bounded from below, the system collapses. So you need that the energy has to be bounded from below. Otherwise, you can always go down in your energy scale. And there is a unique vector that you call the vacuum, which is invariant under the translation. Okay? So, the relativity, so you are constructing your theory this way, and your field should be a complete set of observables. If you apply polynomial of the in the fields to the vacuum, this should generate the whole Hilbert space. Okay, so you have a complete set of observables in your theory. So this positivity of the energy spectrum is the characteristic property of the quantum field theory you are used to in perturbation theory, for instance. And then there are the properties that are implied from the relativistic invariance of the theory. There should be a representation of the Lorentz transformation beyond the representation of the space-time translation. If you are considering, for instance, the theory of one scalar field, you ask for Lorentz covariance of the field, Poincaré covariance of the field. This is the first property that comes from the relativistic invariance of the theory. And the second property is the local commutativity. The field should commute at space-like separated distances. Okay, if you have a field here and a field here, and they are space-like separated, that commutator should vanish. The uniqueness of the vacuum immediately implies that the vacuum is also Lorentz invariant. Because if you commute u of a with u of lambda, this is something like u of lambda minus 1a is 0, and this is invariant, and this is the translation of lambda minus 1 way. This is u of lambda psi 0. So you see that u lambda psi 0 is invariant under translation. But since the state which is invariant under translation is unique, u lambda psi 0 has to be psi 0 also. So invariance under translation imply invariance under Lorentz transformation. First statement. The second statement is that the map x, phi of x, does not exist. Means that this cannot be an operator in the Hilbert space unless it is trivial. This is a consequence of the Poincare invariance of the theory or of the local commutativity. So if you assume the quantum mechanical properties plus invariance under the Poincare group, such object cannot be an operator. It has to be a distribution. It is a consequence of the Lorentz invariance of the theory. It's unavoidable. So ultraviolet divergences come as a consequence of the fact that you assume Poincare invariance of the theory. Okay? This we can show it immediately. So suppose that phi of x is an operator for a certain x. Okay? At another x, you will have u of x minus x bar, phi of x, u of x minus x bar minus 1. These are strongly continuous unitary operators. So if this is an operator, also this is an operator. So if phi of x is an operator for a certain x, it is an operator for any x because of the invariance of the theory. You see what I mean with is an operator? Means that it is point-like supported. It's an operatorial map. Okay? And I'm trying to show you that this cannot be possible. It cannot exist as an operator phi of x. It can exist as average. This means that you cannot measure your field at one point, but you can measure on a space-time region your field. This is a consequence of the relativity principle together with the Heisenberg uncertainty relations, of course. So why? Why is so? If you now compute the vacuum expectation value of phi of x, phi of y, we are making the hypothesis that this is an operator. You can write this like psi 0, u of x, phi of 0, u of x, u of y, phi of 0, u of y star, the vacuum. U of x applied to the vacuum is the vacuum. So you get phi 0, u of x minus y, unitary, phi of 0, the vacuum. And since this is a strongly continuous representation of the translation, and these are operators, this is a continuous function. This has to be a continuous function. If you assume that this is an operator, this vacuum expectation value is a continuous function of the difference variable. Okay? Furthermore, if you if you compute the norm of these point-like supported operators applied to the vacuum, compute this norm, it is an easy exercise to understand that this is going to be this sum. Lambda are complex numbers here. And this being a norm is a positive number. And a function which has this property is called the function of positive type. You see, you give yourself a function. You use the function to build up this matrix. And then you compute these numbers. And because this is a norm, this is a positive number, and the function which satisfies this property is called a function of positive type. And there is a theorem in Fourier analysis that tells you that a function of positive type is the Fourier transform of a positive measure. Furthermore, this function has to be Lorentz invariant. And here enters the key assumption. Yes?
Sorry, when you say the function, do you mean f? Or the
The mu is the measure. The mu.
No, I mean, when you say there's a function of positive type, is the function of positive type f for the expectation?
This is the function of positive type. And being of positive type means satisfying this property for any choice of xi and xj, and any complex numbers li and j, the sum is finite. This is a definition of what is a function of positive type. And there is this theorem which is called the Bochner theorem. It's a fundamental theorem in probability that tells you that if you make the Fourier transform of a measure, a positive measure, so think of a positive measure to be a function times a positive function times the Lebesgue measure, to have a model of it, make the Fourier transform, you get a function of positive type, and all the functions of positive type are obtained this way. But this is not the whole story. This function of positive type is Lorentz invariant. And the Lorentz invariant positive measures are completely classified. The Lorentz invariant positive measures satisfying the positivity of the energy are written this way. P square is the Lorentz invariant. These are all the positive Lorentz invariant measures. Okay? So, you have shown that f we have just assumed that x, phi of x, is a relativistic invariant, a relativistic covariant operatorial map. And we have obtained the result that phi of x has to be of the following form. Is the Fourier transform of a measure which is written this way. P square is P0 square minus P square. And P0 is P0.
And what's rho squared?
Is a function which has constant values on these sleeves, on the mass shells. This function of rho. This is the structure of all the Lorentz invariant positive measure, which are supported in the future cone. I'm using here the spectral property. Okay? If you then, so this is psi. So if you compute f of 0, this is a continuous function, so you can compute f of 0, it's just this integral. But if you do this integral, the value of this integral is a plus b infinity. This integral diverges. Okay? Yes?
What happened to the theta p squared?
The?
Theta p squared.
It is here. It is here. Now compute this integral. You can compute this integral by introducing here a further integral called delta p squared minus 1m squared. And you integrate over dm squared. And you see that this integral equals b times the integral rho of m squared dm squared d3p over p squared plus m squared. And you see that this integral diverges. Diverges unless you choose b equals 0. But if you choose b equals 0, your field is just trivial. Phi of x applied to the vacuum is square root of a applied to the vacuum. So, you see, this is the ultraviolet divergence of quantum field theory. It is a consequence of the spectral condition plus Lorentz invariance. It implies that you cannot measure the field at one point, this state as an infinite norm. Okay? What you can measure are space-time averages of the field. This you can measure. But you can't measure this, and the distributional aspect of the theory is inherent, is an unavoidable consequence of the Lorentz invariance of the theory. We could also prove a complementary theorem. You don't assume Lorentz invariant, you assume local commutativity, and the consequence is the same. So, when you see someone telling to you, I can quantize field theory without renormalization and getting all the results for free, don't believe him. Okay? So the distribution aspect of quantum field theory is not avoidable. It's a consequence of Lorentz invariance, plus the spectral condition. Okay? Yes?
You took an integral over the mass?
No, just this diverges.
No, what is f?
I'm writing this integral in a way you can see immediately it diverges.
But you're taking an integral over m.
Over p.
No, but in the previous line.
Then, I'm rewriting this. Let me show you. Again, I'm writing this integral. It's an integral over d4p. Now I write an identity here. I introduce another variable, another integral over this variable. Okay? I don't need this anymore because m is positive. And then I have theta p0 d4p. This integral, if I do the m integral, I get back to this. Then here I do the p0 integral, not the m integral. This is rho m squared dm squared times the integral of d3p, because I'm doing the integral over 0 over 2p squared plus m squared. Okay. And then if I try to do this integral diverges. at p equal infinity. But this is infinity. Is the ultraviolet divergence in quantum field theory just unavoidable? Okay. Next, let me tell you what I'm doing next week.
So the spectral condition comes from Lorentz invariance.
The spectral condition is the assumption that the measure is only supported in the future. That is an independent property.
If you don't assume that, can you get around it?
No, because I can show this is also a consequence of the commutation relation. It's more difficult to do it. I do this because it's the easiest calculation I can show to you in a short time.
But if it has support everywhere, then this will no longer be true.
I can compensate in that case. I can try to compensate. No, this is just obvious. The second, so let me tell you. So I will review the standard construction leading to the commutation relation. We are today. We have described the classical part of this, but then this is an algebraic feature. The construction of the Hilbert space comes from another splitting of the commutator. Today, we use the splitting of the commutator into retarded and advanced. Okay. This is a X space splitting. This is in X space. This is the commutator. And I have the retarded and the advanced. But if I look to the commutator in P space, I see that there is another splitting of the commutator into the vacuum expectation values, which are solution of the true Klein-Gordon equation, not of the inhomogeneous one. You can see in this case, this has the splitting of the P space commutator. Here I have theta P0 delta P square minus L square, the spectral measure, and here I have the anti-spectral measure, let's say, and both enter in the commutator, and retaining this, the quantization of this, the standard quantization of a free scalar massive field is completely encoded in this. Okay, so our task will be to discuss if I give myself a commutator C of x and y, how many physical interesting solutions are there to this problem, where I'm going to interpret this as the vacuum expectation value. I can summarize the whole problem of quantum field theory in flat or curved space-time in finding solution to this functional equation. And then the standard construction of Birrell and Davis and other books, standard books in which you use the Klein-Gordon product, would be a technical tool to construct such functions. But from the general viewpoint, we have to solve this equation. The standard solution will be reviewed, and then I will tell you, for instance, another important solution in the flat case, which is the KMS, thermal solution. It solves the same equation. The commutator is the same, but these functions are different. So this equation, I will show that there are inequivalent solutions to this equation, and this also will be a proof of the fact that the GNS construction cannot, the Stone-von Neumann uniqueness cannot hold in infinite dimension, because we have counterexamples to it. And then this general scheme will be applied to discuss the examples in curved space-time in which the situation is not at all different. It's exactly the same. If you understand this, once you have constructed the commutator is unique is given by the equation of motion. If you give yourself this equation of motion in a globally hyperbolic space-time, this gives a unique commutator. So the commutator fixed for you the algebra of observables. And then you have to find the splitting of the commutator into this difference. This is the problem of constructing the Hilbert space of the theory. So the two steps are distinct. Here you have a unique answer. The commutator is always the same thing. Here you have many different inequivalent answers describing different physical systems. Okay?